In the previous episodes in the terrain rendering series, we've explored two algorithms for procedural generation of terrains: fault formation and midpoint displacement. In this video, we will take a look at the third option that you've probably heard about, Perlin Noise. This algorithm is very good at generating organic rolling hills and other types of scenery, and is very popular in modern AAA titles. We will tackle it step by step and create a professional level generator in C++, which can be used in both OpenGL and Vulkan. Before we get started, I'd like to say a big thank you to Domenico, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev or by joining the YouTube channel as a member. Okay, same as the other algorithms, Perlin Noise generates a heightmap with values between 0 and 1. In grayscale, the heightmap looks like this. If we scale up the values by some actual height, we can render a terrain. The algorithm visualizes the world as an endless grid of squares. The input to the algorithm is a set of coordinates, 2D in our case. If we pass in whole integers, the point lands exactly on an intersection point. If we pass in fractions, the point lands inside a cell, away from the corners. Every single intersection on this infinite grid is assigned a pseudo-random direction vector called a gradient. Think of these as little arrows pointing out from the corners in various directions. The direction of the vector is determined based on the corner's unique coordinates. The algorithm calculates a value for the input point based on the 4 surrounding arrows. It draws a line from each corner to the input point. It compares the direction of the gradient with the corresponding line using a dot product. And finally, it uses a fade function to blend the results from all corners together. This ensures that as we move from one grid cell to the next, the transitions are seamless, leaving no sharp edges or visible grid lines. Here's a fun fact. The output of the original algorithm in 2D is negative to positive half the square root of 2. The implementation of Perlin in the Unity engine remaps this range to 0 to 1, and in the case of GLM, it's actually -1 to 1. Now, creating the algorithm from scratch can be a bit complex, so the fact that the core is provided by GLM is of great help to us. Enter the Perlin function in the GLM namespace. This function supports input vectors in 2D, 3D, and 4D. We are creating a texture, so we need to input a 2D vector. Let's see if we can develop a complete Perlin solution with it. The function createPerlinMap takes a config structure and updates a vector of floating points. The vector is going to contain the height map of a 2D image. Right now, the config structure contains only a width and height for the height map. There are no limitations to the size of the height map, but using a square of a power of 2 is kind of a gold standard, so that's what we will use. We start by resizing the vector to the width times the height. Now let's traverse the rows one by one, and then the columns. Next we call the GLM Perlin function with a 2D input vector. The X is the current column, and Y is the row. We also need to cast the integers to floating points. The result is set into the output vector using standard mapping from 2D to 1D. We have to multiply the row by the width and add the column. Let's see the results, and we are getting a black texture. The reason is that passing in the current column and row means that we always land on a corner, which means that the distance to this corner is 0, so the result is also 0. But wait a second, what about the other 3 corners? The distance from them is not 0. Well, yeah, but the math actually uses our coordinate offsets along the x and y axes to calculate the blending weights. Because we are sitting exactly at an integer step, our offset along both axes is exactly 0. The fade function turns a 0 offset into a 0 blending weight, completely wiping out the influence of the remaining 3 corners. The final result is always 0. The solution is to sample the spaces between the grid lines, and we do that by dividing the column and row by some scaling factor. This turns them into small fractions, which avoids always landing on the corners. So let's add a scale attribute to the config structure and use it to divide the column and row before calling the Perlin function. Intuitively, you need to think about Perlin Noise as an infinite landscape of mountains and valleys, and the screen as a camera looking down on it from above. When we divide the coordinates by the scale factor, the result is that this camera zooms in and out. When the scale is large, it is as if we are bringing the camera down to the ground. Therefore, the screen captures a tiny patch of the landscape. This makes the transitions gradual and smooth. When the scale is low, we are zooming out and basically the reverse happens. The patterns are now smaller and more repetitive. But the result is still too smooth and doesn't look like an actual terrain. The solution is to stack up multiple noise maps on top of each other. In the Perlin world, a single layer of noise is called an octave. Let's add an octave loop, sum up the results of calling the Perlin function in each iteration, and write the result into the same location. We can see that the mountains simply become taller, but there is no real change to the terrain. The reason is that all these octaves are identical. To make it more interesting, we have to tweak each octave to make it unique. We do that by multiplying the coordinates after the scale factor division by a frequency value. The initial frequency is 1, so the first octave is the same. Now, in each iteration, we multiply the frequency by a new configuration attribute with the horrible name Lacunarity. If the Lacunarity is 1, the frequency remains 1 and there is no change. If it is greater than 1, the frequency increases, which scales up the coordinates in each iteration. This means that we are moving quickly across the noise field, which creates a lot of changes in the height. If it is less than 1, the frequency decreases, which scales down the coordinates. This means that we are moving slowly across the noise field, which creates more gradual changes. The problem at this point is that in each octave, we are still stacking up results from the Perlin function in the range of -1 to 1. To create actual detail, we multiply it by an amplitude value. In general, amplitude is the height of a periodic function. For example, the sine function goes between -1 and 1, but if we multiply it by 2, then it will go between -2 and 2. We start with an amplitude of 1, so the first octave is the same. In each iteration, we multiply the amplitude by a new configuration attribute called persistence. This is usually a fraction, which is less than 1, so the Perlin function result is reduced. This means that we are stacking up octaves of different heights, and the height is reduced from one octave to the next. At this point, the results look very nice, and we can create interesting terrains by playing with the number of octaves, the lacunarity, the persistence, and of course the scale. What we are missing is randomness in the results. GLM Perlin is completely deterministic and relies on a hard-coded array of pre-calculated numbers called a permutation table. To get random results, we are going to move each octave to a different location in the infinite noise field. We do that by generating a vector of vec2 elements, one element per octave. Each element is a 2D coordinate, which is randomly initialized using a very large range. These elements are used as base offsets to the coordinates. As you probably know, the C++ random function is not really random, it is pseudo-random. Therefore, we will add a seed attribute to the configuration, which will allow us to control and reproduce different results for different seed values. We are almost done with our Perlin implementation, and I just want to do a couple of cleanups. First, the implementation will be more robust if the height map is always normalized between 0 and 1. This means that each height map that we generate will actually contain the values of 0 and 1 as the two endpoints of all values. We do that by searching for the absolute minimum and maximum and normalizing each value accordingly. Let's add a variable for the minimum and initialize it to the maximum floating point value, and a variable for the maximum and initialize it to the minimum floating point value. In each iteration, the min value is updated if the current sum is less than the current minimum, and the max value is updated if the current sum is greater than the current maximum. This gives us the endpoints of the vector. After the main loop is complete, we do a second pass over the vector and normalize each value by dividing its delta from the minimum value by the range from the minimum to the maximum value. The result is written back into the vector. As you can see, the result is much more pleasant compared to the original non-normalized version. The second change is much more trivial. Since we are dividing the coordinates by the scale factor, we have to make sure that we don't divide by 0. We add a safe scale variable and make sure its minimum value is 0.0001 or whatever. We use this variable to avoid division by 0. And that's it for today. Thank you for watching, and I will see you next time.